Okay, good afternoon, good morning, good evening, Year 12s. Welcome to our next instalment of videos. This one is about beyond stiffness, exploring the deformation of materials. So we've done Hooke's law. By this point we'll have done Young's modulus, and we now need to think about what happens to materials after they reach their elastic limit. So in this video we're going to discover what happens when a material is elastically and plastically deformed. We're going to compare the elastic and plastic deformation in terms of both the material but also the energy changes. We're going to consider why rubber and other polymeric materials exhibit something called hysteresis, and we're going to examine how the behaviour of materials beyond their elastic limit is influenced by material properties. So to start with, let's think about elastic deformation. Now, elastic deformation is the reversible stretching of the bonds between atoms or molecules. Now, we can think of these bonds as a little bit like little springs. So if I apply a tensile force, the material will stretch because the bonds between those atoms or particles stretch. And if I remove that stretch within the elastic limit, the material will return to its original shape. Just thinking a little bit about the effect of area and also length. If I increase the cross-sectional area, I've got more bonds or mini springs that are in parallel and they're going to resist that stretch. So if I apply a force, I get a little bit less stretch this time because there are more springs resisting that stretch. Take the force off. As long as I'm within the elastic limit, it will return to its original shape. And if I increase the length, of course, I have more springs this time in series that are going to be able to stretch. So if I apply force, I get a much greater extension. So this is just looking at the effect of area and length on how much a material stretches. And this is all within the elastic limit. If we look at elastic deformation, we can either look at it on a force extension curve or on a stress strain curve. So starting with a force extension curve, I apply a force, my material stretches, and when I then remove that force, the material stretches back to its original shape. So the two curves should ideally be on top of each other. Now, if I increase the stiffness in some way, so if I add more springs in parallel by increasing the cross-sectional area, or if I reduce the length in some way, my curve will look a bit like this. I'll get the deformation, and then when I remove it, it will again return to original. Notice that the gradient is steeper, so it's a stiffer object. If I increase the length or decrease the cross-sectional area, I'll get this less steep gradient, and once again, as long as I'm within my elastic limit, when I remove that force, the extension will return to zero. So, just quickly, what do you think this will look like on a stress strain curve? Okay, so if I take a material and I apply a stress, that's force divided by area, I will get a certain amount of strain, strain being change in length divided by the original length. I'll get something like this. As long as I'm within the elastic limit, I get a nice straight line, and if I then remove the stress, it will return to its original shape. And this time, if I change the cross-sectional area or I change the original length, I won't see any change in the gradient of this line, because as you will remember, stress is force divided by area, so I've removed the effects of area, and strain is extension divided by original length, so I've removed the effects of length. So simply changing the dimensions of my object and not going to change the shape of this graph. Now, if I think about energy and work done, you want to think about the amount of energy transferred when you stretch a material. And again, this is all within the elastic limit. So if I stretch the material, I am changing kinetic energy into stored elastic energy. So stretch the material, I do work, I store energy in that spring or that wire. And as long as I'm within my elastic limit, when I let go, this energy is returned to me. I get my extension back to zero, and it's returned as kinetic energy. The spring or the wire moves and returns to its original shape. Now, the energy transferred is therefore the area underneath this curve. And an area under that curve is going to be half times the force times the change in length or extension. The half being because, of course, this is a triangle, and the area of a triangle is half base times height. Now, I know from Hooke's law that the force of this line is represented by the equation force equals stiffness times the change in length. We could swap delta L here for E. Delta L, change in length is the same as extension. So if I put these two equations together, what I find is that the energy E is equal to 1/2 times the spring constant times delta L squared. Just take a moment now and check that you can do that arrangement, please. Okay, so that's all about the energy that is transferred and then returned when I stretch a material within its elastic limit. We now need to think about what happens when I deform a material plastically. So if I deform a material plastically, I stretch it beyond its elastic limit. That means the bonds, or little baby springs, can no longer return to their original shape and they start to break. So the particles start to move past each other and I get permanent damage to the particle arrangement. This looks a little bit like this. First of all, I apply a force. The springs start to stretch. But if I keep on going, I'm going to get to the point where some of these springs have stretched beyond their elastic limit and they're not going to return to their shape, but also the particles have started to slide past each other in an attempt to deal pardon me, with the force that's being applied. So I've got bonds being made with different particles. Instead of this one here, it's being made with this one here because it's slightly closer, and I've got permanent deformation to the material that is simply not going to disappear when I remove the force that I've applied. If I were to chart this plastic deformation on a force extension curve or a stress strain curve, what I would get is initially I would see the elastic deformation, so a nice straight line, but once I reach my elastic limit, so the point beyond which it can't deform elastically anymore, I'd get, and excuse me because I've drawn this with my hand, a curve. So I would see a change. This is no longer a straight line. And when I then try to return the material to its original shape by removing the force, I would actually find that I've got some permanent extension caused because of the plastic deformation. So because those bonds are broken and the particles have started to slide past each other a little bit. Interestingly, this time, if I look at it on a stress-strain curve, I see exactly the same thing. So it's not the area or the length that's having an effect here. It's just that I've gone beyond the point where the bonds can return to their original shape and the particles return to their original shape. So I get some permanent deformation here. Thinking about the energy losses in the plastic deformation, I draw my force extension curve. This is with a bit of permanent deformation, returns to its original shape. Can you please now link the energy lost in deformation and the stored elastic energy that is actually returned? Okay, so the stored elastic energy that I get back is actually the area under this second part of the curve, area A. It'll be a triangle, and it will be this extension minus this extension divided by 2 and times by the force that I reach. But the area inside here, this area B in here, is energy that's actually lost to deformation. So breaking chemical bonds, moving particles, all of that kind of stuff requires energy. And once I've given the material that energy and the deformation has happened, that energy is lost to me. I cannot get it back simply by removing the force. So this here is the portion of the energy that I get back when I remove the force, because some of it will return to its original shape, but this part here is the energy that has been lost to the material because of the breaking of bonds, etc. Now, I want to take a moment just to compare elastic and plastic deformation, and I think this would be a good point for you to pause and make a few bullet points to compare the two types of deformation, please. I've taken the time to do this too, and here is what I've come up with. So, to summarise elastic deformation, you get simple stretching of the bonds between the molecules, and you can think of those bonds a little bit like springs. You don't get any permanent deformation. In other words, all the extension or all of the strain is completely recoverable. I will return to my original length. It only occurs up to the elastic limit on a force extension curve or on a stress strain curve. And all the energy is stored as elastic energy when I stretch the material, and it will be completely returned when I remove the force, as long as I am below the elastic limit. In contrast, plastic deformation. The bonds are stretched to the point of breaking and rearrangement, so I get a lot of rearrangement going on within the material. This gives me permanent deformation. In other words, if I remove the force, not all of that extension or change in length will be recoverable. And this happens beyond the elastic limit. So up to the elastic limit, it will be recoverable, but once I go beyond that point, so once I apply too much force, too much stress, I will get this permanent deformation. And I will get some of the energy back, but not all of it. So some of it will be stored as elastic energy in the material and will be returned, but some of it will be lost to permanent deformation of the bonds and rearrangement of the particles. Okay, we've got two more things I would like to do before the end of this video. The first one is to look at the deformation of polymeric and polymeric materials, so polymers, specifically rubber, things like rubber bands. And then I need to define some key material properties that you're going to need. Now, hopefully, most of you are familiar with the idea that polymers are long chains of molecules all joined together in long chains and then tangled together a bit like spaghetti in the bowl. So here I have got a demonstration of three different chains. I've got a long green chain, a red chain and a purpley blue chain. They're all tangled together. I've actually got some cross links so the chains have been joined together a little bit, but you can see they're all tangled and there's no permanent arrangement. Now, when I try to deform this material, I'll see that it behaves slightly differently to other materials because of this structure. So these long chains of molecules, when I apply a force to this material, the chains will begin to stretch and straighten, and the chains will actually start to rearrange themselves and slide past each other. This means that I get a force extension curve that looks a bit like this. Now notice this is my loading and this is my unloading, and I am coming back to zero extension, so I'm not getting permanent deformation. However, the material is not unloading in the same way as it was loaded, so I don't get these two lines overlapping, I get a difference in these lines. This is something that we call hysteresis. The reason it happens is that energy is being lost to friction, to those chains rearranging and sliding past each other. So if I were to work out the energy that I get back, it would be the bit underneath this dashed line. The energy in here, inside this what we call a hysteresis loop, is the energy that's lost to friction. And if you stretch a rubber band enough times, you'll notice it heats up. That is literally the friction of the molecules rubbing past each other. Interestingly, at this point here, you'll notice that the load starts to get less, which is what I saw in the other materials, but then the force, the stiffness starts to increase again. And this is because eventually the chains go from tangled up to lining up. So they're all in a nice long line, and so the material starts to get stiffer again. That's a little side note, you don't really need to know that, but I think it's quite interesting. Okay, so key thing that we need to know, and that is some material properties. You need to know how various properties change the shape of a stress-strain curve. I'm going to give you a list of definitions of various key properties. I expect you to write these down, and these are your definitions to learn for the materials topic. So first of all, fracture. Fracture is the point at which a material breaks. So the point at which cracks travel through the material and the material actually falls apart. You can have brittle fracture. Brittle is when fracture occurs without plastic deformation. So I only see elastic deformation. Once I reach that elastic limit, it breaks. There is no plasticity. Ductile materials, on the other hand, do deform plastically significantly. So I would see maybe a little bit of elasticity, but a lot of plasticity before fracture occurs. In other words, it will deform a lot before it breaks, which is essentially what a malleable material is. Elastic limit. The elastic limit is the point beyond which the material will no longer return to its original shape. Going along with that, there is also something called the limit of proportionality, and that's the point on the graph where the curve is no longer a straight line. It's important to note that this might actually be slightly different to the elastic limit, despite what I've told you in terms of simplicity recently. So, a material may actually still deform elastically, but not quite follow that straight line. So it could still behave elastically beyond the point of proportionality. Elastic limit is the point beyond which the material no longer returns to its original shape. That is slightly nuanced, and if you want to talk about that in class, we can. Yield point. Yield point is another thing that's nuanced and is very similar to elastic limit and limit of proportionality. It's the point after which there is a large increase in strain for a very small increase in stress. So it's very similar to the elastic limit, and it essentially is the point beyond which the material is plastic, but it's the first measurable point. So when we're doing lots of measurements and we then join up the points on a curve, it's the first point where my measurement actually shows that this has happened. But the elastic limit may well have occurred before that point, it's just that I didn't measure that point. Ultimate tensile strength, normally abbreviated to UTS, that's the highest stress reached before a material fails. And then finally, breaking stress, which is also called the fracture stress. It's the stress at which the material fractures. It's important to note that this might actually be lower than the ultimate tensile stress. Now, I'm hoping you're going to pause